OpenAI has published a new model and the internet is going crazy about it. The model is called Sora. It's a text-to-video model. You input some text and the model generates some video for you. It's very similar to what we have with text-to-music. You have a text prompt and then the model generates some music for you. It's very similar, but of course in a different medium. The results are quite impressive, but there are a lot of questions about it you may have. Like, for example, what can the model do? What are its limitations? How does the model work? What's going to be the impact of Sora in society? What are the threats, the vulnerabilities? And what are some of the ethical concerns that we should have about such a model? Well, in this video, I'm going to try to address all of these questions and more. I'm going to base my opinion and facts off of the technical reports that we got out of OpenAI. It's a quite slim technical report, but there's still enough information to get at least a hint into Sora. Let's get the 10K foot overview of Sora. As I mentioned, it's a text-to-video model. You can come up with a textual instruction, you feed it into Sora, and you're going to get a video out of it that hopefully captures whatever you put into your prompt. Sora can generate up to 1 minute worth of video that's in HD, but the cool thing is that it can also generate videos in different resolutions and with different aspect ratios. So generation is quite flexible. It usually generates complex scenes with a lot of different characters and with a lot of detail. Some of these videos are quite realistic, others are more imaginative, but the results are quite stunning. And finally, there's an important point that OpenAI is pushing. Basically, they say that Sora is a sort of simulation engine. It is a primitive version of a world simulation. Now, this is an important point, and I'm going to try to address this later, but keep it in mind. Sora can be used for different use cases. One, of course, is text-to-video, but there are others as well. So you can use Sora to animate a still image. You can use the model to continue a video that you can feed into the model. And then you can also use it for video-to-video editing. You can, for example, ask Sora to change the setting or the background of a video. This is a stunning example of text-to-video generation done with Sora. Here's the prompt: reflections in the window of a train traveling through the Tokyo suburbs. It's quite impressive. Now, let's take a look at also the other use cases, and for that we'll have to go to the technical report and down here. Okay, so here's an example of how Sora can animate a DALL-E image. So here you have this nice image of a doggo, and here on the right you have the very same image but animated with doggo looking directly at us through the camera. It's quite cool, isn't it? Also, this is another example. So here on the left you have a still image generated with DALL-E of funny monsters, and here you have the animated version of it. Yeah, it's quite cool. Finally, there's another example that's quite compelling. So here's an input video, and here's the edit that we ask to Sora, and that is in this case to change the setting to be in a lush jungle. Let's take a look at this. It's quite impressive. Yeah, because the street is basically like the same, the car's the same, but also the surrounding is more or less the same. The only thing that really changes is the actual background, with here on the right-hand side having a lush jungle. How does Sora work? Well, we really don't have a lot of details about the model, and we really have no detail at all about how the model has been trained. But in the technical report, researchers pointed out the high-level architecture of Sora, and here you have it. The architecture seems to have 3 different components, and these are a visual encoder, a diffusion transformer, and a visual decoder. Now, let's take a look at them one by one. So the visual encoder is a compressor. It basically takes a video and it compresses that video into a latent space. Now let's take a look at this latent space because it's very important. So the latent space is a representation of the original video that still holds information about space and time variables, but it has a reduced dimensionality. It's a compressed version of it. Out of this latent space, researchers extract visual patches that still have information about space and time. And these are units of data that researchers use as the equivalent of tokens in large language models. And so they organize all the information into sequences of visual patches that then they can pass or feed directly into the transformer. And that's basically the second block of our architecture here. It's a diffusion transformer, and that's responsible for the actual generation. As you can imagine, generation happens here within the latent space. So you get as input a sequence of visual patches, and the diffusion transformer gets also some conditioning, like for example a prompt, and then it generates an output that's still a sequence of visual patches. So the entire generation happens within the latent space. And why is that the case? Well, because it is extremely easier to generate the latent space rather than in the original video format, because the video format has a way higher dimensionality. So working with a compressed version of it is way easier. Okay, so once we're done with the diffusion transformer, with the generation, what we do is basically we pass the sequence of visual patches into the visual decoder. And the visual decoder is basically the opposite of the visual encoder in that it reverses what the encoder does. That is basically moving from a sequence of visual patches directly into the video. Okay, so training happens with this type of architecture. So we pass a lot of videos here, then we pass as conditioning, as information, textual information, and these are the captions of the videos that we are training on, and then this is like the entire architecture. Whenever we want to do inference with this, especially for text to video generation, what we do is we drop the visual encoder because it's no longer needed. And all we need here is the initial conditioning, and that is the textual prompt, and then the diffusion transformer is actually going to generate a sequence of visual patches, and those visual patches will be decoded into a full video. At the core of the generation, we have a diffusion transformer. That is a hybrid model that encapsulates a diffusion model within a transformer. For training the diffusion model, what researchers did was basically passing visual patches with noise and asked the diffusion model to predict the cleaned version of those visual patches. At each step, basically, the diffusion model had to denoise the images until it got to the actual clean images, and that's how they trained the model. Well, this is a typical type of training that you would do in diffusion models. By the way, I'm not going to get into the details of diffusion models here because it's very complex. I haven't really addressed diffusion models in this channel, so if you're interested in how they work, just let me know in the comments below, and I'll perhaps dedicate a whole series on diffusion models. If you're interested though in transformer models, I have actually addressed transformer models, and you can find the video that explains transformer models up here. Even if you're not familiar with the technical details of a diffusion model, you may know that diffusion models are really good at generating images. The question is, why didn't they use just a diffusion model? Why did they use also a transformer? Well, there are at least a couple of reasons for that. Reason number one is that video is sequential, is a sequential type of medium. And as we know, transformers are fantastic with sequential data. The reason is because they tend to be quite context aware in the sense that they have memory and they can also learn long-term patterns and relationships. This is extremely important if you want to generate video that makes sense, because the next frame obviously is going to depend on what's happened in the previous frames and also in the frames before the previous frame. So because of that reason, using a transformer is a great idea because it keeps the context and it understands those relationships that are far ahead in time, far back in time. Another reason to use transformers is that they have a scaling property. We've seen this with large language models. That means that the more compute you put into large language models, and the better the quality of the text generated. And this basically happened also with text to video generation. Here we have 3 videos and we basically have the very same prompt, but here on the left we have base compute, here we have 4 times base compute, and here we have 32 times the base compute. And as you can see, the quality of the video generated improves with the amount of compute. Before we go ahead, I just want to introduce the sponsor for this video. It's a course that I make every month. It's called the AI Leaders Blueprint. It's a 3-day crash course on Zoom. It's synchronous. And basically what you get, it's a path towards AI leadership. In this course, you'll learn how to manage AI projects end to end and how to create and nurture thriving AI teams. You'll also learn how you can balance engineering and research while building your AI products. And at the same time, you'll also learn how you can develop models and products that are scalable, reliable, and maintainable. If you are a data scientist, an ML engineer, a software developer, or a manager who wants to get to the next level and become an AI leader, this course is perfect for you. I'll leave you more information about the course in the description box below, where you'll have the link to the course website. I hope to see you in the next iteration of the course. Now, back to the video. Another striking analogy between large language models and Sora is that they both show emerging properties. In the case of large language models, with scale come emerging properties like the ability of the model to generate sentences with a grammar that actually is correct, that makes sense. The fact that the model understands syntax, morphology, and semantics without us, the developers, telling the model what syntax is, what grammar is, or what semantics actually is. So these properties emerge naturally from the scale and from the training dataset during learning time. The very same thing also applies to Sora. Indeed, in the technical report, researchers pointed out 4 different types of emerging simulation capabilities. Let's take a look at them, because they are quite impressive. So the first one is 3D consistency. So basically what this means is that Sora understands how to create a character and move that character in an environment and keeping that character consistent. This may seem simple, but for a model that basically generates videos pixel by pixel, this is like quite the achievement. Another emerging capability is that of long-range coherence and object permanence. This is also quite striking. Let's take a look at this example. So here you see Doggo. The Doggo disappears because you have people who pass in front of Doggo, but then Doggo reappears behind the people because Doggo is still there. This is object permanence, and this is something that for us is a given, but for a model that generates video and that only sees videos as input to its training dataset and captions text, this is quite the achievement. Then there's also another very interesting emerging property, and that is the ability of the model of understanding how characters or how like people, animals, agents can interact with the world. So let's take a look at this example. So here there's somebody painting and this hands painting, and of course here we have the result of that painting onto the world, and that is that the painting is changing because of the brush strokes. Again, this is incredibly hard to tell to a machine, but this machine seems to understand that just like from training. And what we have here is an example of causality, and causality comes into place here because we have time. Of course, video is a format that has time embedded, and that type of time that has embedded is because it has multiple images, one after the other, and so there's a sequence. And so whenever you have a sequence within the real world, there's a sense of time, and of course time comes with causality. If I have my brush and I paint, then the paint itself is going to be on the painting. And so there's the sort of like cause-effect relationship. This is something very difficult to pass onto a model. Here's another example that's quite cool. So there's this guy eating a hamburger, right? And so we can see he takes a bite, and there you can inspect the food after he took the bite, and you can see that there's a bite mark there. This is an example of causality in action. This is quite stunning and quite the achievement. Then also we have another interesting emerging property, and that is that of simulating entire digital worlds. Take a look at this. I'm sure many of us have spent a lot of hours in this game. So this is Minecraft, right? And so Sora is basically able to recreate an entire Minecraft world in a way that makes sense. And so it's able to understand how this world actually works and to simulate it. These are all stunning emerging properties, but I believe that this model goes beyond that. And let me show you what I mean with a video that Sora generated. So I think this video was generated with a prompt like, you have a lady with a red dress moving in the streets of Tokyo. Okay, so now let's think about what it means to generate a video like this. Okay, so in order to generate a video like this, what you have to do is first of all have an understanding of physics. Why do you need an understanding of physics? Well, there are different materials, right? And materials are represented like quite well here. And also the lighting, the way like different shapes and shadows. So you have different shapes and the relative lighting, and also the shadows that form within the frame. And it's quite impressive how all of this works. But this is the level of physics. But then we also have the level of biology. Why do we have the level of biology? Well, take a look at these bodies, okay? So they represent human beings and they look like human beings. And also the way they move is more or less correct. So biology of movement is there. The biology of human bodies is embedded in this video. And we can also go a level up, and that is the level of psychology. So the way, for example, people behave within this scene. Take a look at this lady. So she looks around, she's curious, she looks at the camera, she's pausing, okay? So all of that is part of human psychology. So this shot like conveys a certain level of like emotions and mood. Oh, by the way, let's take a look at that, at the shadows here in the sunglasses. It's quite tremendous job, isn't it? Okay. So this isn't, so we saw that there's also like this psychological level, but we can go a level up, And that is the level of sociology, in the sense of how different people move in a society. And take a look at how people behave, how they move within a city environment. And this looks quite real, right? So you have people just, for example, crossing on zebras there. You have people moving, and all of that feels quite natural. And the last point is that of art, a certain level of understanding of art. And here I mean, for art, I refer to two levels. The first one is architecture, like for example, city landscapes. Here you see buildings that are quite realistic, and they're realistic for Japan, for Tokyo. You have also these signs with language on that, so the cityscaping is done correctly. But also take a look at this shot. This is a movie-like shot, okay? So there is some level of film directing here. The point that I want to try to make here is that Sora has intuition about the world at different levels of abstraction, from the lower levels of physics all the way up to society and art. But the question is this a real understanding? In other words, is Sora a world simulation? Does Sora have a world model just like us, human beings? We do have folk understanding of psychology, of sociology, of physics, of biology. Otherwise, we wouldn't be able to move and navigate the space, the world around us. In my opinion, Sora has a primitive understanding of those levels, because otherwise it wouldn't be able to generate something that works actually quite well. But Sora isn't perfect. It has a lot of limitations. And many of those limitations are limitations in the way it understands the world and all the different levels of abstractions. It has some physics missteps, biology missteps, and some broken causality. Let's take a look at physics missteps first. Here we have the video of a glass lifted in the air, and then it goes down, but it doesn't shatter as you would expect. So the physics of glass shattering doesn't work. You see there, it doesn't work. This is a clear lack of understanding of physics. But there's more. The model has also biology missteps. There's a very interesting tweet of a guy who posted this video generated with Sora. Now let's take a look at this. At first glance, it's super impressive. So you have an ant moving in an ant colony, but there's something that isn't quite right. Let's take a look at the number of legs of this ant. It has 4 legs, but ants have 6 legs, just like any other insect. Here's a problem. So you have something that's very realistic. It almost works perfectly, but it has a major issue, and it's a biological issue. So there's a problem in the world model, in the biology world model of Sora, that doesn't know that an ant has 6 legs. Researchers in the technical report also pointed out that sometimes there are examples of broken causality in the videos that Sora generates. For example, like people eating some food and then not finding the marks, the food marks that you would expect after a person has eaten a piece of, I don't know, of a panini. Despite its limitations, Sora is incredibly impressive, and of course it's going to have a huge impact in society. For sure, it's going to have an impact for creatives. I'm not sure that such a model will be perfect for top creators, like for filmmakers and people at that level. And that's for one reason, and it's because it mainly has this text-to-video approach. So the way you can interact with the model is quite limited, the way you can influence the model. It's something similar with text-to-music models. And these text-to-music models like Musical M are perfect for amateur musicians or people who don't make music, because all of a sudden they have a tool to create some cool music that's personalized to their taste. But this really doesn't work for professional musicians who want to tweak all the different knobs of the musical output. And in this case, I'm sure filmmakers and video makers would like to have more stringent influence over the generation of the model. But of course, like, there's another type of use case that's not text to video, that is video to video editing. And we saw an example of that with Sora, with like that car racing and then changing the background to a lush jungle. Well, that is one of those use cases where I definitely see an application also in top levels of creative industries. But all in all, I think like text to video doesn't provide creatives enough control over the generation. So perhaps we'll need to wait for models that are a little bit more refined for that. There's another major impact of a model like Sora, and that is what OpenAI claims. They claim that Sora can be or will be in the future a foundation model for understanding the real world. In other words, it is a world model or a simulation engine. I agree and disagree with that point. I agree because, as we saw, for sure, Sora has an understanding of the world at different levels of a reality, of representations of reality, but at the same time, that understanding is flawed, and I don't know if that's going to be fixed with scale. So just by pumping in more data and more data, then the world model is going to all of a sudden be perfect. On this point, I feel closer to Ian LeCun's point of view. He argues that in order to create a representation of the world, a world model, rather than dealing with generative models, we may deal with models that are not as detailed and that work at an intermediate or a more abstract level of representation that doesn't entail working out all the details and all the pixels there. Let me give you an example. It's easier for a model to generate an ant with 6 legs when it has a higher level of understanding of what insects are on an abstract level, and the model knows that insects by definition have 6 legs, and therefore ants have 6 legs. It's easier for a model to do this rather than inferring directly from pixels that ants have 6 legs, and then use that information that derives from the level of pixels to generate ants with 6 legs with all of its details. As you can imagine, a model like Sora can be used for nefarious reasons. For example, you could use such a model to generate deep fakes of politicians during an election. So there are clear safety threats. What's OpenAI doing to address those safety threats? Well, they are approaching the issue from different angles. First of all, they are collaborating with partners, experts like filmmakers, like video makers and other people, so that they can experiment with the model and do adversarial testing and report the feedback to the researchers in order to fix those vulnerabilities. The second approach that they want to employ is that of filtering. We already have an example of filtering with ChatGPT. Whenever you input a prompt in ChatGPT, there's a filter that analyzes your prompt and it checks whether it adheres to OpenAI's terms of service. If it doesn't, then you don't get an answer. They want to do the very same thing also with Sora at the moment they release this product to the public. Finally, OpenAI wants to encapsulate metadata directly in the generated videos. This metadata is going to flag that video as AI generated. Beyond safety threats, I think this model once again brings to light ethical problems that we have not just with OpenAI, but also with large tech companies that are basically pioneering AI development. What's in the training dataset? Is there any copyrighted material? And if that's the case, have the copyright owners been paid? This wouldn't be surprising given OpenAI has likely used copyrighted data for its previous language and image models. Another major problem I see here is that everything is closed source, not just the model itself or the weights of the model. Well, that's the least of it. The problem is that we don't even know the specifics about the architecture. We don't know anything about training. The only thing we know is that they did training on a godly amount of data, but we don't know anything about it. And I think this is a problem because these models are extremely powerful and we need to know how they've been engineered to have a better understanding of their vulnerabilities. It's clear by now that it's basically impossible for all companies out there, apart from big tech, to compete on AI innovation in foundation models. The reason is quite clear: computation and access to data. This leads us to the last problem, that is OpenAI has an incredible amount of power. This power concentration is extremely problematic. It's basically a monopoly. At best, it is an oligopoly. Thinking that we have a monopoly in a space as pervasive as AI that's going to revolutionize everything we do, it's scary. Here you have my breakdown of Sora, or at least of what we know about Sora. I hope you got a lot of value out of this video. If you did, please give a like to the video. If you want to get more videos like this, consider subscribing. That's all for today. I'll see you next time. Take care.